All right, this is going to be our walkthrough for the assignment titled Related Rates. So our first one here, we've got gas being pumped into a spherical balloon at a rate of 5 feet cubed per minute. So the first thing I would do is I would look at this and say the rate is 5 cubic feet per minute. That's a rate of change with respect to time of the volume. I can tell that just based on the units, 5 cubic feet per minute. We want to find the rate at which the radius is changing, right? So we want to find dr dt. That's what we're looking for, the rate of change of the radius, when the diameter is 18. Right? If the diameter is 18, then of course that's going to mean that our radius is going to be 9. Right? And since this unit up here is in feet cubed per minute, 9 inches, we really want to convert that into 3/4 of a foot so that all of our units match up when we go through and do this problem. So now we just need to use the volume equation for a sphere, which is volume equals 4/3 pi r cubed, and take the derivative with respect to time of both sides here, giving us dv dt equals not 4/3, we're going to take the derivative. The derivative of 4/3 pi r cubed should be 4 pi r squared dr dt, because we're doing it with respect to time. Then we just plug in all of our values. dv dt is 5. Our radius is 3/4, and we're looking for dr dt. And so all we really have to do here is just, don't forget to square that, right? 3/4 squared. And so all we have to do here is just simplify this down and solve for dr dt. So looks like we have 5 equals, we've got 4 pi times 9 over 16 times dr dt. We can cancel out a 4 here with the 16 and make that a 4, which is going to then, when I multiply by 4, give me 20 equals 9 pi dr dt, or dr dt is equal to 20 over 9 pi. This is a radius, which was in feet, and it's per minute, because that's how this was changing. So our change of our radius is 20 over 9 pi feet per minute. For our next one here, we've got a 20-foot ladder leaning against a vertical building. So I'm immediately just going to draw a picture. The length of a ladder doesn't change, so I'm just going to call that 20. Okay? Remember, we don't want to put anything in the picture that's changing, but the length of the ladder won't change. The bottom of the ladder is sliding away from the building, right? So in this x direction. And we've got then the top sliding down, which would be in the y direction. And we're interested in how this is changing when the y value is 8. Right? It says when the ladder is 8 feet from the ground. And it's sliding away horizontally at 3 feet per second. Right? And so that means that our dx dt is going to end up being 3. Right? And it's a positive 3 because the length of x is changing as that ladder slides away from the wall. So all we need to do is write an equation that involves both x and y, which will just be our Pythagorean theorem, x squared plus y squared equals 400. We can then just take the derivative of this with respect to t on both sides. So 2x dx dt plus 2y dy dt is equal to 0. And we're looking for how fast the ladder is sliding down. That's dy dt. So we've got almost everything that we need here, right? We've got our y value, but we don't have an x value. So we'll need to go and figure out what that x value is. We'll do that in just a second. So we have 2 times whatever x is, times dx dt, which we do know is 3, plus 2 times our y value, which is 8, times our dy dt, which is what we're looking for, is equal to 0. And of course, we do need to figure out what our x value is, right? We can just use x squared plus y squared equals 20 squared, or x squared plus 64 is equal to 400. which gives us x squared equals 336. Well, that means that x is the square root of 336, which simplifies to 4 root 21. So now we'll just solve for dy dt. Shouldn't be that bad here. The 2 times the 4 here is an 8, and this has also got an 8. So when I bring those over and simplify, we should be able to cancel out those 8s, right? So really what we're going to end up with is just dy dt is equal to negative 3 root 21 divided by this 2 right here. I will subtract this to the other side and then divide by 2. And our units here are feet per second. So for our next one here, this is kind of a classic problem. We've got a light that's at the top of a 16-foot pole. So here's 16 feet, and there's our light at the top of the pole. And we've got a boy who's walking away from the pole. He's 5 feet tall. I know my scale is not anywhere close to accurate here, but that's fine. And he's walking away from that pole at a rate of 4 feet per second. Right? And so that means that this distance here, the rate at which he's moving away from the pole is 4. So dx dt is going to equal 4. Now we also have this length, which is the length of his shadow. So we want to know at what rate is the tip of his shadow moving, right? And we also want to know at what rate is the length of his shadow increasing. So the length of his shadow is just y, right? But the tip of the shadow is x plus y. So we're going to write that y is the shadow, and x plus y is the tip of the shadow. So we need to figure out both of those rates of change, right? So in order to do this, we need to recognize that this is a similar triangle situation. Those are right angles, and they both share this angle in common, right? So the ratio between y to 5, right, y over 5, should be the same as the ratio of x plus y to 16, right? And we've got a couple options here. I think the easiest way to go about doing this is just to cross multiply to begin with, right? We get 16y is equal to 5x plus 5y. Or in other words, 11y is just equal to 5x. When I take the derivative of this with respect to time, right, we'll end up with 11 dy dt is equal to 5 dx dt. Well, we want to find dy dt, right? Dy dt is the length of the shadow, how quickly it's increasing. So we'll just say that dy dt is equal to 5 times dx dt, and we know dx dt is 4, and then we'll divide it by the 11 that was in front of the dy dt. So that'll be 20 over 11 feet per second. And then in order to figure out what the tip of the shadow, how it's increasing, right, well, that's just going to be dx dt plus dy dt. Right, this is the tip of the shadow. Right? This is the shadow itself. Right, so that's just going to be 4 plus 20 over 11. Well, that's just going to be 64 over 11 feet per second. Right, so it's increasing more quickly because he's moving and the shadow is also lengthened. And that's it for number 3. For our next one here, we've got the top of a silo, which is a hemisphere, has a diameter of 20 feet. So I'm gonna sketch that out. So here's my hemisphere. I'm gonna do this. I guess we'll do it in red. That's fine. So here's my hemisphere. It's got a diameter of 20 feet, right? Which means that the radius here is 10 feet. And we'll note that this rate of change we're given later on is in inches per hour. So let's just call that 120 inches for that radius there. And then what we have going on is we have that it's coated by a layer of ice, right? And so we've got a layer of ice out here, right, that is coating this hemisphere. And that ice is melting, so the thickness of that ice is decreasing at a rate of 1/4 of an inch per hour. And we want to know how fast the volume of the ice is changing when the ice is 2 inches thick. So we're going to call the thickness of our ice here x, right? And then we're going to be looking for how fast the volume is changing when dx dt is negative 1/4 of an inch per hour, right? And so what we need to do then is we need to write a formula that represents the actual volume of the ice, right? Because that's what we're looking for. How fast is the volume of the ice changing? Well, the volume of the ice ought to be the big hemisphere of ice minus the inner hemisphere. So the big hemisphere is going to be, it's a hemisphere, so it'll be 2/3 pi times the radius cubed. Well, our radius is 120 inches plus x. So this will be 120 plus x cubed. And then we have to subtract from that the volume of the inner hemisphere, which is just going to be 2/3 pi times 120 cubed. And the nice thing about this is I don't even care about simplifying out that 120 cubed and the 2/3 pi times that, because all we're going to do is we're going to take a derivative here, right? We're going to do dv sub ice dt is equal to the derivative of this function over here with respect to t. Well, this over here is a constant, right? So when I take its derivative with respect to any variable, it just goes away. And so what we're left with here then is, well, 2/3 pi times the 3 is just going to be 2 pi times 120 plus x to the second power times the derivative of 120 plus x, which is just 1, and then multiplied by dx dt. So then we just need to plug in the information that we have. We know that we're interested in what's going on when the thickness of the ice is 2 inches. So we'll plug in 2 for x, and we'll plug in negative 1/4 for dx dt, and that dv sub ice dt is just going to be 2 pi times 120 plus 2 squared times negative 1/4. And I'm not going to bother going through the arithmetic. 122 squared times 2 divided by 4 with a negative there is going to be negative 7,442 pi inches cubed per hour. And that's how fast the volume of the ice is changing. All right, for our next one here, we've got a water trough. And it's 8 feet long, and it's got bases that are equilateral triangles whose sides are 2 feet long. So I'm gonna just sketch this out. So what we've got here is we've got an equilateral. Ooh, that was not even close to equilateral. We've got an equilateral triangle here, and here's the trough going back, right, for some animal to eat out of or drink out of or whatever. Well, that looks really bad too. Let's try and do that again. Something like that. And this is 8 feet long. We know that's not changing. And we know that this side here is 2 feet, this is 2 feet, this is 2 feet. Those aren't changing. But what's happening is we're filling up this trough, right? And so we're trying to figure out the rate at which the water level is rising as we pump water into the trough at 5 cubic feet per minute. So dv dt is going to be 5. So what we want to be able to do here is we want to be able to write the volume of this trough in terms of the height of this equilateral triangle, right? Because what's happening is it's filling up with water, right? And so it's filling up with water. We want to know at what rate the water level is rising, so that's a change in this h value here. So normally, what we would do here, right, is we would use our volume formula for an equilateral triangle, right, because volume is s squared root 3 over 4, right? And then we're going to multiply it by, it's not volume, but the area of the equilateral triangle is that. And then we're going to multiply it by 8 for the length of the trough. So in other words, our volume is just equal to 2s squared times root 3. But what we really want is we want to figure out what's going on with the height. So we have to do a little bit of right triangle trig here, right? If we draw this triangle here and then the equilateral triangle inside of it, right? We know that this h that we're interested in, and we need to figure out some ratios going on here, right? And we know that this is 1 unit here, right? And we know that this is 2 units here. So we should be able to use the Pythagorean theorem to figure out what, and I do this in a different color here, to figure out what this length is, what that actual full height is. Because then we should be able to come up with some ratios that we can use. So we would just find that by doing, we'll call it L. L squared plus 1 squared equals 2 squared. So L is going to be root 3. Right, so that is root 3. So that gives us a nice idea of how these ratios are working. Right, it tells us that the height to the side length here, right, the height to the side length, h over s, should be equal to the height of root 3 to the side length of 2, which tells us that s is equal to, if we cross multiply here, right, we'll get root 3 times s is equal to 2h. So s is equal to 2h over root 3. And so we should be able to then plug that in for our s, giving us volume is 2 times 2h over root 3 squared times root 3. And if we simplify that down, we'll end up with the volume is now equal to 8h squared. And then we're going to end up with a root 3 times a root 3 in the denominator, which will cancel with one of the root 3's in the numerator, with the root 3 in the numerator. So we'll end up with the volume is 8h squared over root 3. And so now we've got the volume written in terms of the variable that we want to find the rate of change of. So what we'll do is we'll just go to a new page here. Using volume is equal to 8h squared root 3. We'll take the derivative with respect to time, getting 16, this was not 8h squared root 3, it was 8h squared over root 3. So 1 second here. We'll get 16h over root 3 dh dt. Then we'll just plug in our values. So we knew that dv dt was 5, but we didn't have a value for h yet. So let's quickly go back over here. We need to figure out what the height is when the depth of the water is 8 inches, right? So that's actually, it does give it to us, right? 8 inches in feet, right? That'd be 8/12 of a foot, which would just be 2/3 if you divide those both by 4. So we're going to plug in 2/3 for our h value. And now we should be able to simplify this down. So we're going to have, well, it just looks like we're going to multiply by root 3 here. So we're going to have 5 root 3. And then we're going to also multiply by this. This 3 is going to drop to the denominator, so we'll multiply it by 3 also. And then we're going to divide it by 32 to get our dh dt. So dh dt is going to equal 15 root 3 over 32 feet cubed per minute. Okay, for our next one here, we've got the area of an equilateral triangle decreasing at a rate of 4 centimeters squared per minute. So first, we're just going to write out what's the area of an equilateral triangle. Well, we know that now. It's s squared root 3 over 4. And the area is decreasing. dA dt is negative 4. And we want to find the length of the side, or how fast the length of the side is changing when the area is 200. And so we're interested in an area being 200. So we'll get dA dt when we take the derivative. Not much work here to set this one up. dA dt should just be the derivative of this, which is going to be 2s root 3 over 4, or just s root 3 over 2 times ds dt. Now we know what dA dt is. dA dt is negative 4. And we don't know what s is offhand yet. And we're looking for ds dt. So we do need to figure out what s is. So we're given that the area is 200. So what we need to do is we need to just go in and say, well, 200 is equal to side squared root 3 over 4. Or the side squared is equal to 800 over root 3, right? Or s, the side length, is equal to the square root of 800 over root 3. Well, root 800 is the same as 200 root 2 over the square root of the square root of 3. Well, that'd be 3 to the 1/2 to the 1/2, or 3 to the 1/4 power, so the 4th root of 3. So what we need to put in here, I guess I clearly did not leave enough room here, is 200 root 2 over the 4th root of 3. Then we'll solve for ds dt. So when we do that, that's like 200. It's not 200 root 2. Let's fix that. That's 20 root 2. All right, the square root of 400 is 20. So this is just 20 root 2 over the 4th root of 3. And so we'll just solve for ds dt. So we'll multiply by the 2, right? Multiply by the 2. In fact, we'll do this on a new page because we're kind of already running out of room here. So we've got negative 4 is equal to 20 root 2 over the 4th root of 3. And we also had a 20 down there, so 20 times the 4th root of 3, and then times the root 3 also that was in the numerator, and then a ds dt. So this is what we're trying to simplify down. 20 over 2, of course, is just going to be 10, right? So we can do that right off the bat, right? So we're going to have negative 4 equals 10 root 6 over the 4th root of 3 times ds dt. And then we'll multiply by the 4th root of 3. So we're going to have negative 4 times the 4th root of 3 over 10 root 6 equals ds dt, which will just simplify to negative 2 times the 4th root of 3 over 5 root 6. And our units in this problem were centimeters, and the time frame was minutes. So we get negative 2 4th roots of 3 over 5 root 6 centimeters per minute. And our next problem here, we've got the ends of a horizontal water trough, which are 10 feet long. These are our isosceles trapezoids. And the lower base is 3 feet, the upper base is 5 feet, and the height or the altitude of it is 2 feet. Similar thing to what we were doing a couple problems ago with the equilateral triangle. The water level is rising at 1/4 of an inch per minute. And we're looking at when the depth of the water is 1 foot. So first I'm going to just sketch what the trough looks like in general, right? It's just a trapezoidal prism here. Right? With a length here of 10 feet, we know that this is 3 we know that this upper portion here is 5, and we know that this height here is 2. So that kind of gives us an idea of what it looks like. Now it's filling up with water, right? So of course, as it fills up, all these values are changing, right? So it's filling up with water. And the 10 feet that's the length of this trough doesn't really matter other than with the volume. What we really need to look at is this isosceles trapezoid here as it fills with water. And so what we're going to do is we're going to break it down into a rectangle and 2 right triangles, right? So if I do that, we know that this isn't changing. This is going to be 3 no matter what. And across the top, right, this is 3. And if I've broken this down into equal pieces, those are each going to be 1 since the whole thing was 5. And so from there, we should be able to do a little bit of work knowing that the entire altitude here is 2. So we should be able to figure out a bunch of different things about this. But what we really need to know is like how the height here of this thing is related to the other pieces of it. So we can see that there is a similar triangle here. There's a right triangle and a right triangle, and they share this angle down here, right? This angle right here. And so we should be able to say that whatever this little distance here is, I'm going to call it A, that 1, and I'm going to call this little height here H, that 1 to 2, the ratio from this leg of the right triangle to this leg of the right triangle, should be equal to the A to H ratio, right? Which tells me that A is equal to H over 2. So once I have that A is equal to H over 2 here, I should be able to kind of come up with a full, nice little formula for my volume, right? And so my volume is going to be 10 for the length times the area of that trapezoid as it fills up. Well, the area of that trapezoid as it fills up is this rectangle in the middle, which I'm going to kind of sketch in green here. This rectangle here is 3 times H, right? And then we're going to add to that 2 of these triangles that I'm going to sketch in red here. And I have 2 of these triangles. So that's going to be 2 of these 1/2 of the base times the heights, right? And so the base is going to be this value A, and the height is going to be the H value that we're looking for. And so now we can see how useful it is that we found what A was in terms of H. So we should just be able to plug in that A value of H over 2. Right? So as we rewrite our volume formula, we're going to have 10 times 3H plus the 2 times 1/2 is going to go away. And so it's just H times H over 2, which is H squared over 2. We can distribute the 10 through if we want, giving us 30H plus 5H squared. And when we take our derivative of that with respect to t, we end up with 30 dH dt plus 10H dH dt. And so I can just factor the dH dt out of both of those. You don't even really have to write it twice. You can just do, since the whole thing is all in terms of H, you can do 30 plus 10H dH dt. If you want to write them next to it, that's fine too. And then all we have left to do is plug in the values that we know. Now the height that we're interested in is, let's see, the height we were interested in was when the depth of the water was 1 foot. So we care about when H is 1. So, and then we're looking for dV dt. So dV dt is going to be 30 plus 10 times 1, right, which is just going to be 40, times our dH dt. Now our dH dt is 1/4 of an inch per minute, but everything else is in feet. So 1/4 of an inch per minute as our dH dt, right, should be the same as 1/48 of a foot per minute, right? Because, you know, there's 12 inches in a foot. And so we'll multiply this by 1 over 48, which gives us 40 over 48, which will reduce down to 5 over 6. And again, our units are feet, and it's volume, so feet cubed per minute. So our next one here is we've got sand leaking out of a hole in a container. It's falling onto the ground, forming a conical pile, so it's going to look like a cone. The altitude, or the height of it, is always the same as the radius. So I'm going to just make a note of that. The height is equal to the radius for our cone. Okay. The height of the pile is increasing at 6 inches per minute, so that'd be dH dt is 6 inches per minute. And we want to find the rate at which the sand is leaking out, which would be a change in the volume, when the height is 10 inches. So we'll just set this up as volume is equal to 1/3 pi r squared h, because that's the volume of a cone. We want to do this all in terms of h because we have an h value and a dH dt value. So we'll just replace the r with h, giving us volume is 1/3 pi h cubed. When we take our derivative, dv dt is going to be pi h squared dH dt. And all we have to do is plug in our 10 and our 6 for h and dH dt, giving us dv dt is pi times 10 squared times 6, which is just 600 pi inches cubed per minute. And our last one here, we've got a stone that's being dropped into a lake, causing circular waves. The radii are increasing at a constant rate of 0.5 meters per second. So dr dt, the rate of change of the radius, is 0.5 meters per second. We want to know at what rate is the circumference changing when the radius is 4. So we want dc dt. This is actually going to be our easiest question here. The circumference of a circle is just 2 pi r. So when I take the derivative, the circumference is 2 pi, dc dt is going to be 2 pi dr dt. So all we have to do to find dc dt is just plug in dr dt. We don't even care what the radius is. 2 pi times a half is just pi. So we have pi meters per second. And that is the end of our walkthrough of the homework assignment called Related Rates. That's it.